And Nikhil, just as a confirmation, you're gonna share video also while you're doing a screen share?
Yeah, I have it in a presentation style format here in my apartment, but I'm
Yeah.
going to be sharing the screen as well.
Okay, great. Okay, well, as Dr. Orozco's is calling in, I think we can get started since I'm going to give a few minutes intro anyway. So it's really a great pleasure for me to uh, be here to introduce Nikhil's for his PhD defense. Nikhil is the first student that I actually took on as a PhD student when I joined UCSD back in late 2015. So he's basically been through it all with me, which is why this is such a special event, and it's quite a long time coming. The kind of the start of it is where I think the first two things that were in my lab was a robot, which I bought off eBay, and then Nikhil, who I said, figure out how this robot works, because I personally had no idea how to put it together. And that was kind of a test to see, like, this PhD student that I was recommended uh, by another faculty member, how good was he? And so just by pure kind of determination, Nikhil, as a single, uh, solo engineer, was able to get this really complicated surgical robot that was, mind you, purchased off eBay, and it was purchased as a scrapyard junk um, pile. Basically, they didn't think it was working, and so I said, I think it's gonna work. Why don't you try to make it work? And Nikhil actually got it to work, which was just amazing. So that's how I figured that this was going to be a good PhD student. And since I said he's been there from the beginning, my group has changed over the past several years, but you'll see that he's basically at the center of all of the he's at the center of all of the group photos. He's really been the core of the the group, and I was trying to find some pictures of Nikhil working hard in the lab, and really all I could find was these photo opportunities where it doesn't really show that he's doing anything except playing with toys. But he does work really hard, and it's just been quite a journey from him starting to work on hardware like this robot to him starting to understand the more theoretical aspects of the work. And eventually you're going to see what he's developed, which is really fundamental and really impressive. And oftentimes, I know it was really hard on him. Might have been some casualties in the lab, but everything was fun, and he got to make many friends. And it just seems that in his off time at UCSD, he's been very active, and it's really great to see the friendships that has been formed with him and his peers. And of course, we've had a great opportunity to travel with him, and it's just been impressive to see him grow as both as a presenter of the types of research he does, but also as an individual researcher. So without further ado, Nikhil, please take it away. Looking forward to the talk.
I think you're muted, Nikhil.
Hey, sorry, I'm just trying to get this working again. Cool. All right, thank you, Michael, for that intro. As Mike already said, my name is Nikhil Das. I'm currently a PhD candidate at UCSD in the electrical engineering department. And I wanted to talk about my defense topic today, which is learning-based robot configuration space modeling. Sorry. So I wanted to begin with a background of what exactly is configuration space. And then I want to formally define what the problem I've been working on is. The majority of my talk is going to be about the three main contributions throughout the past few years, which is first, Fastron, the forward kinematics kernel, and distance estimation using Gaussian processes. So I want to go through some background of what exactly is configuration space by taking you through an example of what motion planning is. So the idea of motion planning is pretty easy. You have a start and you have a goal, probably some obstacles on the way. And all you need to do is connect the start to the goal without intersecting with any of the obstacles. So that's pretty easy. But what if your point robot is now actually a rigid body? It's some body with some volume to it. If you try executing that same path, you're going to run into some problems. Namely, you're going to run into some collisions if you try to execute that same path. So what can we do instead? What we can try doing is we can pad the obstacles and consequently shrink our robot down to the size of a point. If I try redrawing that same exact path I drew previously, you'll see that it intersects with the padded obstacles. So we can throw that one away, and we can instead try to find a path that circumvents the padded version of the obstacles. Now we can go back to our original problem, which was the unpadded versions of the obstacles. We can enlarge our robot back to its original size. And as we run that path that we get, it should be collision-free. So this was pretty straightforward. We just took our robot and we shrunk our robot down to a point, and we also enlarged our our environment. So let me try to generalize what we just did. We took our workspace, and then we made something called a configuration space. In configuration space, each point in this space represents a unique robot configuration. A configuration fully defines every point in the workspace for that robot. If I were to query the configuration space, which means I'm just going to pick different points in the configuration space, that can actually give me validity statuses in the workspace. So in this case, any of those red dots on the right side, if they end up inside one of the padded obstacles, that means my robot in that specific configuration in the workspace is going to be in collision. Similarly, you can say the same thing about the green points and being collision-free. So now how can we take the same concept and do this for more complicated robots? Namely, how can we do this for robot manipulators or robot arms? So we can try doing the same thing here. So in this case, we have now a 3 degree of freedom robot arm. It's 3 degrees of freedom because it has 3 joints that it can actuate. There's 2 joints on the table and 1 joint that I'm going to call the elbow joint, which is near the top of the robot as it's currently displayed. In the configuration space, each axis for a robot manipulator corresponds to one of the degrees of freedom. So in this case, since we have 3 degrees of freedom for the robot, we're going to have 3 axes in our configuration space. In this case, we have a base pitch, a base yaw, and an elbow pitch. And using those 3 axes, we can now convert our rigid body robot into a single point in configuration space on the right side. So I can take this complicated robot from the left and just represent it as a point. Similarly, those cubes that are on the table are going to actually transform as well. So the green, red, and purple boxes are going to turn into these weird amorphous blobs, which unfortunately for d-dimensional configuration spaces where you have, for example, 6 or 7 degrees of freedom in your robot arm, these blobs are going to be very hard to make. So the way that most people approach doing any type of planning or solutions in configuration space is they take a sampling-based approach. For example, for sampling-based motion planning, what you can do is you can grow a tree in the configuration space. And for every node of this tree, you're going to assess the validity in the workspace. So for sampling-based motion planning, you're going to grow the tree. And every time you grow a node in the tree, or you add a new node to the tree, you're going to perform some type of collision check. If the collision check returns that it's collision-free, you're safe to grow the tree in that direction. But if you get a in-collision sample, you're not supposed to grow the tree in that direction. And using these trees, you're able to get some type of motion plan. So what exactly is involved in a collision check for a robot? So let me take you through one example. So let's say you have one configuration in mind, or you have one node in your tree in mind. First, you need to locate where the arms are going to be. So you need to identify where the meshes of each link is going to be. You need to do the same thing with each obstacle. If you have a complicated obstacle or a non-convex obstacle, you might need to break it up into easier to work with obstacles. And then for every link obstacle pair, you need to somehow assess whether those two bodies are going to be in collision. And remember, we're doing this for a single node in the tree. Obviously, this is going to be computationally expensive in motion planning because you need hundreds to thousands of collision checks for a single motion plan. In fact, collision checking can take up to 90% of sampling-based motion planning time. This is an obvious bottleneck, so we need to come up with some way to mitigate this approach. So let me summarize what collision checking is, what we expect from it. So for a single node in the tree, we're going to input a robot configuration. So this can be represented as a d-dimensional point, where d represents the number of degrees of freedom of your robot. You pass it into some black box collision checker. This black box should spit out some collision status, either in collision or collision-free. To say this in a different way, we want to make some validity checking configuration space model, where we input some configuration, put it into some model, and it spits out a configuration-based metric. So this could be the collision statuses that I described in the previous slide. It could be distance to collision. It can tell you whether or not you can reach a certain target. So it could be anything that's dependent on your configuration. It should be able to try to model that. So taking this black box approach, the question now is, can we actually learn a model, f of q, to serve as a proxy to this computationally expensive validity checking? To be more explicit, the problem that we're facing is that planning or trying to find solutions in configuration space requires hundreds to thousands of samples. And for each one of these samples, you need to do some type of computationally expensive validity verification for each sample. So the approach that I'll be discussing in the remainder of these slides is how can we accurately and efficiently model the configuration space for a robot. Now, I can't claim that I'm the only person in the whole world that has worked on this problem. For example, there have been some machine learning approaches to trying to model the configuration space. For example, there's an algorithm called support vector machines. And for this specific implementation, what they did is they fit a decision boundary based on support vector machines between each link and obstacle pair. And they compose the support vector machine model so that they get some composite configuration space model, which is shown on the bottom right here. Well, this model can work successfully for robot manipulators. It has some issue because for each link obstacle pair, you need to make a new model for that, which might be a computational burden in itself. Another approach is to use Gaussian mixture models. And in this case, they run multiple sampling-based motion planning algorithms to get their data. The points that are in collision and collision-free are both fit with their own respective Gaussian mixture models. And then these Gaussian mixture models can either be used for sampling or for identification of the collision status for a new query configuration. A disadvantage with this approach is that you need to run this sampling-based motion planning algorithm around 5 to 10 times before you actually converge to a usable solution. And additionally, as with most Gaussian mixture models, which is a parametric model, it cannot always adapt to the complexities of the configuration space obstacles. And third, a hot topic is neural networks. Recently, there is a paper that proposed clearance net, where in this case, they took parameterized versions of the environment and they trained a model. They trained a model so that they can predict the distance to collision or collision statuses. With this approach, they were able to get 95% accuracy for collision statuses. However, a problem with this approach is that, as with most neural network approaches, it requires a lot of time and training data to actually develop a model. And also, this model has only worked so far in parameterized environments. So if we want to broaden it to other environments, we'll need to somehow restructure this neural network. Another approach used contractive autoencoders, where they took a point cloud representation of the environment, and then they used that point cloud representation to perform collision checking. A downside to their approach is while they are able to get a broader representation of the environment, meaning that they don't have to parameterize the environment, a problem with this approach is that their accuracy is only up to 70%, which may work well in some cases, but we can probably make that accuracy higher. So with all the related works that I mentioned, there is at least one of these issues that the remainder of these slides I'm going to try to address. So some of the issues might involve you need a lot of data, or you need many models to represent your model, or it might be slow to query. You might not have good accuracy, and it might not be adaptable to a changing environment. So the three main contributions will be shown on this slide. First, I want to talk about Fastron, which is a configuration-based model, configuration space model for proxy collision detection. And an example is shown on the right side. Then I developed a new similarity function that I call the forward kinematics kernel. And using that, I'm able to get better similarities between two different configurations that I'm trying to compare. And thus, that gives me a better Fastron model. And finally, rather than just doing binary collision statuses, we can actually get a different metric, which is distance to collision. And I want to approach that using Gaussian processes. So let me start with Fastron. So to reiterate what I've been talking about, I want to get some configuration space model that takes in a configuration and produces some collision status. So the requirements for this model should be, first, it should be fast to query. I want it to be fast to query because if it's not fast, then there's no point of modeling the configuration space in the first place. I want it to be fast to train. I don't want to move my robot to an entirely new environment and then spend hours just trying to learn how to work in that environment. Instead, I want to be able to move the robot to a new position, and it should be able to take only a few milliseconds to develop a new model. Speaking of which, I want the model to be adaptable to a changing environment. So let's say you're working on a table, and then you move a cup over a few centimeters. I don't want to have the model have to retrain from scratch, but instead I want to be able to update a pre-existing model. And finally, I want this model to be risk averse. To give you an example of what I mean by risk averse, let me highlight two different errors that the model can make. One type of error, the robot thinks that it's collision free, but it's actually in collision, which is shown on the manipulator on the left. However, if it thinks that it's in collision, but it's actually collision free, that's not as bad of a scenario. So I want to emphasize true positive rate so that I can count for the difference in these types of errors. I want to try to emphasize the true positive rate. So here's the pipeline of how Fastron actually works. So I first begin with a data set of randomly sampled robot configurations. And then I pass it through some ground truth geometric collision detector. That gives me a labeled data set for each sampled configuration that I have. And finally, I pass it through some model update procedure that fits a model to my sampled configurations that I can then use to query for proxy collision detection. So here's how the Fastron model works. I first identify some special points in my random set, and then either raise or lower those special points, depending on their collision status. And then I threshold that entire model. I threshold it, and anything above that threshold is considered in collision, while anything below that is considered collision-free. Mathematically speaking, this is just a weighted sum of kernel functions. A kernel function is just a fancy name for a similarity function, or in this case, I'm trying to compare a query point Q to a point in my data set X sub I. For each of these kernel functions, I'm going to assign a weight to it. And then for each point in my data set that has a non-zero weight associated with it, this is going to be considered a support point. This is the special points that I've been talking about. The support points are what is raised and what is lowered. So how do we actually find these weights? So I developed a novel way to train this fast-run algorithm. Oops. Sorry, let me accidentally click the wrong spot. So some useful things with this fast-run training algorithm is that I'm going to be using greedy coordinate descent, lazy kernel matrix evaluation, a conditional bias parameter, and redundant support point removal. And I'll explain these in the following slides. So I choose to use coordinate descent to promote a sparser solution. With a sparser solution, that means I can get faster query times because I'm comparing my query point to fewer samples in my training set. And the way that coordinate descent works is I pick some value in my weight vector, and then I adjust it according to how wrong that corresponding training point is. I'm considering it greedy coordinate descent because I choose the descent direction according to which point in my data set is considered most incorrect. I won't go into too much of the details here, but a nice thing that comes out of this greedy coordinate descent approach is that there's a upper bound on the maximum number of iterations that takes to converge to a solution. In practice, however, we usually don't hit this upper bound, and it only takes a few hundred training iterations to actually develop a model. Another byproduct of the coordinate descent approach is that I can now perform lazy kernel matrix evaluation. So with most kernel-based algorithms, you might need to compute the entire kernel matrix, which is an n by n matrix, where n corresponds to the number of elements you have in your training set. The nice thing about Fastron and using coordinate descent is that you never actually need to compute this entire kernel matrix all at once. Instead, you can do it lazily and compute one column at a time. And in fact, in most cases, I don't even compute the entire kernel matrix by the time that the model is done training. Instead, I only compute a subset of the columns of the kernel matrix, which actually saves a lot of time. In the interest of getting a risk-averse model, I want to emphasize the true positive rate. And I can do that by conditionally biasing my target values. And I can do that by introducing a conditional bias parameter on the target values that are considered in collision. So if I increase the influence of those points, you can see that I increase the true positive rate. However, that comes at a cost of decreasing the true negative rate. So you can play around with this parameter depending on how risk-averse you want your model to be. And finally, in the interest of making an adaptable and efficient model, I want to remove the points that are no longer considered important. So for example, if your environment changes, like if you move a cup on a table, your data set is correspondingly going to change. And thus your decision boundary separating in collision from collision free will also change. So when that happens, you might move your decision boundary. For example, move it to the middle as shown here. And that might leave a lot of redundant support points, which are all the red dots on the left. By removing those that have the highest chance of being correctly classified after their removal, we could actually clean up the decision boundary, the support set, but leave the decision boundary pretty much as is. So this gives me a much sparser solution even when the environment is changing. So this summarizes the forward pass of the Fastron pipeline. But as I just mentioned, we want to be able to adapt to a changing environment efficiently. So I'll be employing a active learning approach where I take my current model and I develop a new smaller set of configurations so that I can try to track the changes in the environment. So the point of active learning is to reduce the overall amount of sampling required. I don't want to have to resample my entire space every time a cup on a table moves. Instead, I want to try to do this efficiently. So the way I'm going to do that is I'm going to take my support set and re-perform some collision checks on those just to see if my model is currently fine. And then I'm going to exploit this model by sampling near each one of these support points. The point of this exploitation stage is that if I move an object a tiny bit, I'm going to assume that the changes in the configuration space are always also going to be changed a tiny bit. In other cases, however, I account for these using an exploration stage. In the exploration stage, I try to account for drastic changes by performing uniform random sampling in the remainder of the configuration space. So this can account for newly introduced obstacles in the workspace, or it can account for drastic changes in the obstacle's position. So I made Fastron to be a faster proxy collision detector, and I compared it against two geometric methods. FCL, the flexible collision library, is considered one of the standard collision checking libraries for robotics, and GJK is an approximate geometric method. And as the name implies, Fastron is fast. It does perform about 5 times faster than the FCL method. In terms of true positive rate, you get a 90% true positive rate with the Fastron algorithm, which is pretty close to the geometric approximation GJK. So this is a fairly risk-averse model. However, there's a downside to Fastron, which is it might be a little too risk-averse. The accuracy goes up to around 70-ish%, which is not very high. The problem with not having a very good accuracy is that if you make your model too risk-averse, you might not have enough room to actually do any planning in. So this might actually hurt you in the long run. So what we want to try to do instead is we need to somehow increase the accuracy of this model. And I do this by the development of the forward kinematics kernel. So there's something I realized with this approach to modeling configuration space. And that is I'm treating the configuration space and the workspace as two completely separate entities, while in fact they're actually very much related to each other. To be more specific, an isotropic radial basis function kernel loses the joints influences that are perceived in the configuration space that should appear in the workspace. So let me give you an example. Take this robot here. If I move my elbow by 30 degrees, according to the radial basis function kernel, moving my elbow by 30 degrees is no different than moving my wrist by 30 degrees. That should not be the case because obviously changing these joint angles may have different effects in the workspace. So I need to come up with a better way to relate the configurations in the configuration space to their positions in the workspace. So let me give you an example of what the radial basis function looks like by taking a look at these 3 robot configurations on the left. So I want to compare the pink configuration to the blue one, and also the green one to the blue one. As you can see on the right, we have a radial basis function plotted in the configuration space, where the radial basis function is centered on the blue configuration. According to the radial basis function, the pink and the blue have the exact same similarity as the green and the blue. And that can be seen because the pink and the green exist on the same isocontour as shown on the right. So according to this radial basis function kernel, the pink and the blue are just the same as the blue and the green. But as you can see on the left, there's a big difference between the blue and the pink and the blue and the green. The green is way out to the left, while the blue and the pink are very much close together. So what I'll do instead is I'll apply the radial basis functions in the workspace instead. And that gives me a different forward kinematics kernel, which is shown on the right side. As we hoped and expected, the pink and the blue robot configurations are now considered very similar to each other, as they both exist in the 0.8 isocontour as shown on the right. However, the green one is way dissimilar than the blue and the pink, and that's because it's beyond the 0.2 isocontour, as once again shown on the right. So the main part of the forward kinematics kernel is the forward kinematics equations. And what forward kinematics does is it takes your position in the configuration space and maps it to some points in the workspace. So for example, if you have your robot currently at 60 degrees and negative 30 degrees, which is shown on the left, I can perform forward kinematics equations that can produce select points along the robot manipulator in the workspace. And using these forward kinematics equations, I can now define the forward kinematics kernel. As you can see, it's just a sum of radial basis function kernels evaluated on different points selected along the arm. In all of my experiments, I chose the control points to be at each end of each link. So each kernel produces implicitly some feature space. And I wanted to illustrate why the forward kinematics kernel provides a more intuitive distance metric for proxy collision detection. So I can approach this visualization using kernel PCA, or kernel principal component analysis, which identifies the most important components in your feature space. So here I'm trying to work with a 4 degree of freedom robot arm, and I'm trying to plot the top 2 components taken from the feature space of each of these kernels. In this case, each color represents the type of obstacle that the robot would be colliding with for that specific configuration, while the red dots correspond to collision-free configurations. As you can see from the middle plot, the forward kinematics kernel has a very high degree of separability without even doing any type of transformation with your data. This is just kernel PCA, where I'm trying to visualize the data as best as I can. However, according to the RBF kernel, all these colors are muddled up together, which gives you an intuition of what the RBF kernel is trying to do when it's trying to separate the classes. So as you can tell, the forward kinematics kernel might have an easier time of separating the classes versus the radial basis function kernel. So thus, I applied the forward kinematics kernel to my previously proposed fast-drawn algorithm, and I get some surprising result, which is the query time is less than before. Even though I'm doing more work per kernel, I get a faster query time. And the reason for that is, using this new kernel, I require fewer support points to represent my model. But more importantly, however, is I successfully increased the accuracy of the model by a significant margin. So it went from around 74% accuracy with the previous kernel to over 95% accuracy. So now that I can use this as a proxy collision checker, I can now apply this to a wide array of sampling-based motion planning algorithms. So as you can see, using the forward kinematics kernel and fast-drawn for providing collision checks in sampling-based motion planners produces faster motion plans across the board. And this is all thanks to swapping out the kernel from the radial basis function kernel to the forward kinematics kernel. So the nice thing about the forward kinematics kernel is that it's a valid kernel that can be actually used in other kernel-based applications. So I already showed you what kernel PCA might look like if you want to visualize your data, for example. But you can also do kernel discriminant analysis, where you identify in your feature space the direction to best project your data so that you can get maximum separability between your 2 classes. And as you can see here, there's much better separability with the forward kinematics kernel versus the radial basis function kernel. Or third, we can apply it to import vector machines, which retroactively assigns class probabilities to each point in your data set. But what I want to show that is even cooler than that is applying the forward kinematics kernel to Gaussian processes for the purpose of distance estimation. So far, I've only talked about proxy collision detection, where I provide a binary collision status, either in collision or collision-free. So there's an example of what the fast-drawn algorithm might produce, either a binary status between collision and collision-free. However, distance to collision may be an informative metric. And the reason for that is, for closer proximities to collision, that may suggest a more risky scenario. So there's a few applications for distance to collision estimation. One of them could be for robotics trajectory optimization. You could provide some type of haptic rendering, and that might be useful in, for example, virtual reality or teleoperated or simulated robotic control. So for example, in surgery, if you're manipulating some tissue, you want to be able to get some type of force feedback. Otherwise, you might over-penetrate the tissue when you might not mean to. And third, you can calculate realistic collision responses in either simulations or video games. For example, in Angry Birds, you want to be able to hit the obstacles without, or by, sorry, you want to be able to hit all the obstacles and you expect it to behave realistically. So for robot manipulator, this is how we're going to define the geometric distance to collision. As with the collision detection, first we want to identify where the robot arms are going to be. In this case, I'm going to identify each unique link as R1, R2, and R3. I'm going to do the same thing with each obstacle that I have on the scene. So these three apples are labeled O1, O2, and O3. And I'm going to compute the pairwise distances between each of these items. I'm going to take the minimum of each of these pairwise distances, and that's going to be my representation of what the distance to collision is for a specific configuration for a robot arm. There's some issues, however, with this approach, that it could be computationally expensive, just as with the case with collision checking with the binary case. Additionally, the sensors that these distance estimates are based on could be sources of uncertainty or of noise. These sensors could be depth sensors or camera sensors, but in either case, there's some noise associated with these sensors, and we want to be able to account for that. Thus, we need to make a model that is not only fast to query, but it should also be accurate, and it should be able to account for the uncertainty in our sensors or in the model. So this is where regression models can come into play. Regression models can model a continuous scalar output. The assumption with regression analysis is that the measurements that we achieve are actually the sum of the true value that we're trying to measure plus some error term. Most of these regression models focus on modeling the expected value, or the value that we expect out of these sensors if they were noise-free. So for example, if we have this random set of points, we can try performing regression analysis, and we can, for example, fit a line to it, or some polynomial curve. Or if you want to get non-parametric, you can perform kernel regression, and you can take a weighted sum of kernels to try to fit some nonlinear model to your data. Another approach, however, is Gaussian process regression, which, unlike the previous models in the previous slide, not only calculates the expected value, but also produces the covariance of their predictions. So the expected value can be used for prediction, just as with the other regression model cases, but the covariance can be used as a measure of uncertainty. Here's some math representing each of these values, and I'm going to walk through a little bit of what's going on here. So we begin with our noisy example measurements. For each point in our data set, we're going to compare it to our query points. And we can do that comparison using our similarity functions or our kernel functions once again. And then you're also going to try to account for the noise by adding the variance of the noise in our model. So this noise can either be known in advance, or it can be estimated as a hyperparameter during Gaussian process training. So obviously, Gaussian processes have some power associated with them. They can not only model the expected value, but also their covariance. And obviously, the forward kinematics kernel was powerful because it significantly increased the modeling accuracy for a robot manipulator's fast-draw model. So what I want to see is, can I combine the powers of the Gaussian process with the forward kinematics kernel? And I did so on a 7DOF robot, which is shown on the top right here. Comparing the Gaussian process with the forward kinematics kernel to other regression techniques, we can observe that there's far lower error compared to the other techniques. All these models were trained on only 500 samples, and for a 7-dimensional space, 500 samples is not very much. So that actually goes to show that the Gaussian process with the forward kinematics kernel is extremely powerful, even with only a few samples. So the forward kinematics kernel applied to the Gaussian process yields very accurate measurements and actually orders of magnitude faster distance estimation values than the geometric methods, up to 70 to 80 times faster. So now I want to see if I can apply our distance estimation technique to some application, namely trajectory optimization. So for trajectory optimization, you might approach the problem like this, which looks like a lot of math, so I'm going to try to break it down. All we're trying to do here is we want to find the shortest possible path with the largest obstacle clearance, all of that within some constraints. For the obstacle clearance objective, I'm going to supplant the distance estimation with each of the model-based approaches to see if I can get faster trajectory optimization times. So what we see here is the ideal case, where I optimize with the geometric method without any noise associated with it. So this is the perfectly observable case where I don't have any sensor noise at all. This is what it looks like when I'm using the Gaussian process with the forward kinematics kernel as my distance estimation technique. Based on the end effector trajectories, which are shown in green and red, we can see that the final results are fairly similar to each other. The Gaussian process method is very similar to the ideal case. However, it takes around 10 times less time for the Gaussian process kernel to find this solution compared to the ideal case. If I were to use the distance measurements directly, without any type of modeling, I'll get something like this. The black dotted curve here shows the original trajectory that I'm beginning my optimization from. And you can see that the final result, that the noisy measurements for optimization, you can see that there's not much difference between the original and the new motion plans. So in that noisy case, it doesn't do very much in terms of optimization. Using other kernel-based approaches, those two methods do very well in terms of trying to optimize the path length. In these cases, the path is pretty much straight. It's very close to being straight. But the part that these two methods miss out on is the clearance part. So the reason that it actually penetrates straight to the obstacle is because the accuracies of these two regression techniques are so low. So far, I've only talked about using the expected value from the Gaussian process, but there's something else that I liked about the Gaussian process, and that was its measurement of uncertainty through its covariance. I can measure the confidence in the Gaussian process's predictions using one-sided confidence intervals. And those confidence intervals are based on the expected value and the covariance that are produced by the Gaussian process. So the underlying distribution that Gaussian processes are based on is a Gaussian distribution. And the concept of confidence intervals tries to find a certain amount of area under the Gaussian curve so that they can assign some level of confidence for your predictions. So in this case, if I want to be 95% confident of my prediction, I want my mean to be 1.64 standard deviations above my value. So what this confidence interval says is that for this specific case, I'm 95% confident that my true distance to collision is going to be greater than 0 as long as my mean is 1.64 standard deviations greater than 0. And I can plot each of these confidence intervals for the two different types of Gaussian processes that we have, the one based on the Gaussian kernel and the one based on the forward kinematics kernel. The black dotted curve represents the true distance equals 0 contour. And as you can see here, the forward kinematics kernel performs much better in terms of trying to fit to the true contour where distance equals 0. On the other hand, the Gaussian process using the Gaussian kernel has these weird pockets of undeserved confidence or confidence placed in random places, like in the top right corner. And I think the main difference between these two results is all thanks to the forward kinematic kernel. But now we can actually do something cool with this confidence interval. We can actually develop a hybrid model that switches from Gaussian process-based predictions to sensor-based predictions when the model is not confident in its predictions. For example, I can define a 95% confidence model where it takes Gaussian process-based predictions if it is 95% confident in that prediction. On the other hand, it can take an averaged approach to modeling the distance to collision based on the sensor values. And we try applying this to a case where there's a narrow passage. So in this case, what we can see here is the robot is fairly confident in its distance estimations when it's distance from the obstacle. But when it goes between the obstacles, there's a higher risk of being incorrect about their predictions. So the model switches from Gaussian process-based predictions to an average sensor-based prediction. We can see on the right side that there's 3 different curves there. The cyan curve represents the Gaussian process-based predictions, while the red curve provides the true distance to collision using a noise-free geometric method. As you can see there, the cyan and the red curves are pretty close to each other up until the vertical line. That vertical line represents the switch that occurs from the Gaussian process-based method to the sensor-based method for the hybrid model. If you follow the yellow curve, which is the hybrid model's predictions, it matches the Gaussian process-based prediction in the beginning, but then it switches over as soon as the dotted cyan curve, which represents the confidence, drops below a certain value. Thus, the hybrid model can get a very accurate measurement of distance, even when the proximity to collision is very low. So to conclude, the 3 main contributions I talked about today were Fastron, which is a proxy collision checker, the forward kinematics kernel, which is a similarity function designed for robot manipulators, which drastically improved the performance of the Fastron algorithm, and finally, distance estimation through Gaussian processes. These are some of the publications I've worked on. And with that, I'd like to thank my committee, first the chair, Dr. Michael Yip, Dr. Atanasov, Dr. Kreutz Delgado, Dr. Martinez, and Dr. Roscoe. I'd like to thank you for your time and helping me with this final defense. I'd like to thank especially Dr. Michael Yip. As he mentioned at the beginning, the first task that he gave me was trying to set up this robot. And I admit that I was very scary, but I'm very thankful that he trusted me with this very expensive machine. And throughout my entire PhD career, he has given me so many opportunities for me to grow. For example, with the makerspace or with grant writing, he's given me so many things that I would not have dreamed of doing. So I'd like to thank him for all of that. Also, all of the rest of ArcLab and all of my friends, I'd like to thank them for making the last few years much more fun and entertaining and academically engaging. And the people that are sitting next to me, my family, my sisters who've already got their doctorates, but they're rooting for me still. My mom, who always supported me and always believed in me, and also my dad, who introduced me to the world of science and technology. So with that, I'd like to open it up to any questions. Once again, those are my main contributions, and I'd like to thank you for your time.
Great. Yeah, we'll have time for questions now. I think best thing to do maybe is to just do a raise hand in Zoom, and then I'll call out, or Nikhil can call out the person that raised their hand.
Michael, there's usually two parts. There's the part where questions, general questions from the audience,
Yeah, exactly.
are requested, and then there's the part where it's the committee.
Right. So this is the general audience part, and then after these questions, we'll close, or we'll have the audience leave, and then we'll have the general committee. Does anybody have a question from the audience?
Also, if you want, you can put it in the chat, because for me, at least, it's kind of hard to see who raises their hand.
All right, Naman has a question.
I have a question regarding slide 56.
All right.
So there, I think you're talking about the trajectory optimization and the switch happening between the distances. And my question is, how does that switch happen while I'm doing the trajectory optimization online? Do you always choose the one that is having lower confidence?
So I'm the one that is actually doing the distance estimation. So I could either keep querying my, what's it called? The Gaussian process method, or I can switch to a sensor-based method. So these sensor-based methods, I'm assuming are based on a camera model or some depth sensor. So what I'm going to be doing there is I'm just going to keep querying those sensor values and recalculating my distances.
Okay, got it. Thanks.
Florian has a question.
Awesome presentation, Nikhil, as always. I just wanted to ask about, it is called Fastron. How can we make it faster? In particular, what do you think about like parallelization efforts, and how would they fit in better into the current or future motion planning stacks that you foresee?
So I worked very briefly with parallelization, and this is actually ongoing work with some other students, but let me show you what I've worked on so far. So with sampling-based motion planning, between two nodes, you also have to check what's between the two nodes, and that's called an edge. So with edge checking, what most people do is they go iteratively along the edge in the configuration space, and they perform collision checks on each one of those. So while I say that collision checking is slow, it's actually, a lot of that is due to the edge checking part of it, where you're iteratively checking along the edge. So in this case, I applied this to a GPU. And let's see. Sorry, this is smaller than I thought. So I apply Fastron to a GPU, and GPUs are graphical processing units. And that allows you to do some type of parallelization. And as you can see here, the collision checking time for various batch sizes is actually much lower when using the GPU versus the CPU-based methods. And on the right side, we have some motion planning times with and without the CPU. Sorry, with and without the GPU. So this is something I worked on only briefly, so I don't produce a paper out of it. However, there's some students that are currently in the lab that are working on other forms of parallelization, for example, multi-threading in the using the CPU. So yeah, we're already thinking about parallelization with Fastron.
Any other questions? So Nikhil, could I ask, how would you actually foresee somebody that was developing a robot to get started with implementing Fastron? Like, what would they need to do? Like, or what conditions would be ideal to implement Fastron?
So we do have code online. This is not, I haven't tested it too much yet, so I don't know if it's like easy to follow the steps, but at least the algorithm is written up online. So if you wanted a place to start, you can go on our GitHub page and you can try downloading what we have on there. Other than that, I tried to outline the algorithm very clearly in the paper itself. So you can pretty much translate the pseudocode line by line, and you should be able to implement Fastron yourself. But other than that, I did have a block diagram earlier on in the slides where you pretty much need to supplant each of those blocks with first your black box collision detector, so you can choose how you want to do that. A lot of people use FCL, which is part of the Move It motion planning framework. You can use that for your collision detection. The model update, you can either download our code online, and for the active learning, you can, I also have another set of pseudocode where you can just employ what I've written there to make your own version of Fastron.
Mm-hmm. And you mentioned that you need, like, basically this is all based off of data, right? So the items that we're collecting the data, you said are cameras or maybe depth sensors, anything else? Or is that?
Probably, yeah, any way that you can get any environmental information.
Mm-hmm.
So I think you can, yeah, you can use depth sensors, cameras. Well, you can use the Vicon system for, like LiDAR, for example. So pretty much any way that you can get some type of environmental information and locate where your obstacles are going to be, that allows you to do some type of ground truth geometric collision detection, would allow you to get that collision checking black box as part of the Fastron pipeline.
And do you need to know, do you have to be able to see the entire environment?
You don't have to see it. So there's another group for that. What they did was they, for a given depth image, they assumed that anything that was behind or anything that was occluded by the obstacle is unsafe to move in. So you can make that same assumption and just call all of what's behind an obstacle as in collision.
Right.
Renal
has a question.
You don't have any other information behind the obstacles.
Right. Renal?
Yeah, you had a slide, and I don't remember the slide number, but it was about translating your proxy collision checks into actual sampling-based motion planning algorithms. And on that slide, it was actually showing that RRT-based variants of sampling motion planning were slower using the RBF kernel than GJK and FCL. Is there a straightforward explanation for this, like the lower accuracy is requiring you to redo collision checks, or what is kind of holding back the Fastron model here? And I know the Fastron FK model is doing better, but
so
do
yeah,
you know why that discrepancy is?
In the very first paper where I proposed Fastron, the second bar was actually much lower, and the reason for that was because I just chose simpler environments. But as I moved to more complicated environments where I'm forced to actually move around obstacles much more like circumventably, the Fastron RBF actually struggled with that case because, as I mentioned on one of the earlier slides, the Fastron RBF model can actually be a little too risk averse. So that doesn't very much leave me much room to actually do any type of planning in. So the reason that Fastron RBF is struggling in these environments is because the model is actually a little too risk averse, and there's actually pretty much no room to do any collision-free motion planning in, according to that model at least.
Cool. And sorry, small follow-up question. In the collision checks, we were seeing like 5 to 6 times speed improvement of Fastron FK over the other collision checking methods. But here in the motion planner, we don't see that same thing. Is this because of the overhead of the motion planner from other computations?
So there is some overhead. So even though like I'm claiming 90% of the time is dedicated to motion planning, dedicated to collision checking. Some motion planning algorithms are more efficient in terms of their sampling. So collision checking might take a little less time in other motion planning algorithms. But also something I'm not showing in these bars is a verification stage and a replanning stage. So for at least the approximate methods for GJK, Fastron RBF, and Fastron FK, there's actually 2 other colors that are within each of these bars that should be shown, which is the amount of time it takes to verify whether a path is actually collision-free according to some ground truth method. And if that path is incorrect, I need to actually replan using the ground truth method around the erroneous part. So I'm actually trying to make it simpler here by not showing all those different stages within each bar. But the reason that it's not 5 times faster, whatever I claim the collision checking improvement to be, it's not that much faster because there's also various stages within the motion planning bars that I'm showing here that are not actually being displayed.
Great. Thank you so much for your presentation.
Thank you.
Okay, I think we can take, if anybody has one last question, I think we can take that. Otherwise, does anybody have one last question? Okay, I guess we'll leave it there for the general audience. Again, yeah, thank you, Nikhil, for a great presentation.
Thank you, everyone, for listening.
Yeah.